Okay, great. So let's start the last lecture of Daniel's mini course about the boundary of the stability manifold. So please,
Okay.
Daniel.
Okay. So yeah, you can hear me, right?
Yes.
Okay. All right. So right. So just just to recall where uh so um basically I've described this construction of this compactified a partially compactified stability manifold. And the idea is that the objects here on the boundary points are multi-scaled lines. Well, it's real multi-scale decompositions.
Multi-scale decompositions, multi-scale stability, whatever.
Well, I called them augmented. We were calling them multi-scale stability conditions, but then unfortunately, a few weeks ago, someone put a paper on the archive defining something called multi-scale stability conditions. So,
Oh, all
so
right. So you
I think that
urgently.
I think that that's the best name for them. But now we're calling them augmented stability conditions. I'm open to suggestions if someone has a better name. But
Yeah, I think multi-scale stability. I mean, it's actually multi-scale decomposition plus some stability type of data, like
exactly, yeah,
analogously to Bridgeland. So yeah,
exactly, yeah.
okay, multi-scale stability. Okay,
Yeah. Anyway, whatever. But yeah. So uh. Anyway, the points of these multi-scale decompositions. So um. So this was our notation. So they along with a sort of marking function, like what you're saying, with the log central charge. Basically, for each terminal component, it's a map from this corresponding subquotient category CV minus 0 to the smooth part of that component. Um, so that's that's the data. And I wanted to just in this picture here, just where this is again the example of stat P1, and I mentioned I just wanted to make it a little bit more concrete what these points correspond to. So here, what does this correspond to? It is a line it's a multi-scaled line that looks like this. So there's a root node, and then there's two bubbles. And the point is that the log central charge of O lives in one of these bubbles, and of O of 1 lives in another bubble, like this. And the continuous data here, okay, you have this, each of these components is isomorphic up to translation to C, these minimal components. But the additional little bit of data here that you have is basically 2 points in the plane that say they differ by. So you have this 2 points in the plane that differ by some complex number alpha. And this configuration of points is sort of defined up to scaling. And the whole thing is sort of defined up to translation. So this configuration of points is defined up to translation by C and up to scaling by a positive real number. So basically, you can think of alpha as living in S1. And what this line at infinity is basically it's the universal cover of S1. So, you know, in this, right. And so this region, let's say here, so if this is where the O attaches, oh wait, let me put, if this is where the component corresponding to O, make it a little bigger. If this is where the component corresponding to O attaches, and this is where O1 attaches, well, here the imaginary part of alpha is positive, and that's saying that O has a much larger phase than O of 1, which is why it corresponds to a point in this interval here. So as alpha varies in this interval, this is like, yeah. So really, it's more like alpha is equal to e to the I pi y, where y is the height. It's just the coordinate it's just the y coordinate in the diagram. So here, let's say, you know, this is 0 and this is pi. And so what's basically happening is that the alpha is you know, the alpha is e to the I pi y, it's varying between 0 and pi. And then the interesting thing happens, let's say at this point. So this is the point where, so maybe I've drawn this kind of funny. Anyway, it's roughly speaking, this is the point where the imaginary part of alpha I think actually this should be maybe minus I pi y to be precise. Just the way I've drawn it. So this is the point where alpha, pointing from O of 1 to O, lies just along the negative real axis. In other words, this is the point where O it's the same curve. The curve, all that's happening is that these two connecting points on the root component are rotating around each other, but they hit these special points where the what do you call it? Like the displacement from one of the connecting points to the other is a real number. And in this case, this corresponds to the mass of O is very, very small.
May I ask you kind of maybe a question, because
Mhm.
yeah, I mean, in this dB Koch on P1, there are many chambers, yeah.
Yes.
And do you kind of consider all of them when you compactify, or you just some
What do you mean
kind
by
of
chambers?
chamber? Well, for example, if I choose a T structure which correspond to the Kronecker quiver,
Yeah. Mm-hmm.
yeah, so it's one chamber. If I choose a chamber which correspond to coherent shifts, so we're in dimension 1, it's another chamber, and kind of.
That's what I've drawn. I think the red and the blue the different blue bulbs here are the different chambers. Yeah. I think.
Yeah, okay. And where is a quiver chamber in this?
Each of the blue things is a quiver chamber.
Is each of the blue? Yeah,
Yeah,
okay.
they're all sort of equivalent to each other.
By shifts. Oh, well,
yeah, by a shift. Like you get the same algebra, I guess, right?
Yeah.
Yeah, so it actually gives you the same quiver description, but it's just the actual way that it's identified with objects in the category is a little different.
Okay. All right.
Yeah. Right. So, yeah, so this, I just wanted to explain this a little bit more, how you actually see it. And if you want to know, if you have a path that's going like this, basically what's happening along this black path is that inside the stability manifold, So along this path, what happens is, well, you start in the red region, which corresponds to slope stability, and then you cross into one of these chambers where the only stable objects are O and O minus 1, the way I've drawn it. And these just remain stable for all of the rest of time. And if you look at the log of the central charge of O for O minus 1 in that chamber along that path, hold on. Okay. This looks like one of these things will look like alpha t plus some constant beta plus o little o of 1. So basically the log central charge of the two stable objects, maybe it's better to call this beta 1 plus beta naught, and the log central charge of O1. So if let's say you go along this path, that's what we've been talking about, we'll have some asymptotic expansion. It will be sort of beta prime 1 t plus beta naught prime plus O1. And what I'm calling alpha in that in the description above, alpha is really just the difference beta 1 minus beta 1 prime up to scale, because alpha is really only defined up to scale. And so that's the idea, is that if you want to find semiorthogonal decompositions in the derived of a derived category, let me just create some more space for myself here. Right. So if you want to find semiorthogonal decompositions, which is something we want to do. I mean, what I just got at the first day, we're looking for these sort of canonical semiorthogonal decompositions. Well, you should be considering paths in the stability manifold, for which the sort of stable objects have these kinds of asymptotics. So stable objects have these sort of well-defined asymptotics, and in fact, you can consider these 2 points. Like in Alekos's talk, these are 2 functions of t, and if you consider that as 2 points in C, so you consider that as marking P1 as the trivial multiscaled line with these 2 marked points corresponding to the log central charge of O and O1, and as it limits to infinity, you get exactly that multiscaled line at infinity with the 2 markings of O and O1 somewhere on those components. So that's the picture. And now you can say, well, exactly which SODs appear in this partial compactification? It's exactly those for which all factors have stability conditions. So the idea here is that this partial compactification will allow you to probe different semiorthogonal decompositions, but by its nature, it restricts you to only the semiorthogonal factors that have stability conditions. And part of the slogan is that maybe that's actually kind of a good thing. And I'll try to explain a little bit more why that's true. But the idea is that maybe these are the ones that you kind of, the natural semiorthogonal decompositions are ones that come from paths in the stability manifold that exist on the boundary of the stability manifold.
By analogy, with the T-star, I mean, this semi-orthogonal decomposition, by definition, the missing stability from the very beginning, like T structures missing
Right.
stability. So maybe
Right.
adding stability, yeah, it's a good idea.
It is a good idea. Yeah, it's like I mean I've said that you can study birational geometry without like considering ample divisor classes, but you can't really do the minimal model program without considering ample divisor. You can ask if two non-projective varieties are birationally equivalent, but there's not like really a good theory for how to approach that. So you introduce Kaehler classes, and all of a sudden that helps you to make sense of birational geometry. So in the non-commutative setting, non-commutative birational geometry really basically should be the study of semiorthogonal decompositions such that all the factors admit stability conditions. That's kind of the slogan. And I will explain a little bit of, so this alleviates certain things. So for instance, there was this, people who are thinking about Dubrovin's conjecture, it's kind of, this is the conjecture that generically semi-simple big quantum cohomology is equivalent to having a full exceptional collection. It's a very intriguing kind of conjecture, and lots of people have thought about it. And in general, people have thought about finding different classes of varieties, studying different classes of varieties with full exceptional collections. But a problem that comes up there is this existence of phantoms issue. So you can, there are surfaces. There were these Godot surfaces, and then recently there's this like really remarkable result that if you blow up P2, I think it's at 10 generic points, then you can do this thing where you find an exceptional collection of line bundles that has the expected length, but they do not generate the derived category. So they give you a basis in K-theory. It's exceptional collection of line bundles, but they don't actually generate. Another way to think about that is that you can have a semiorthogonal decomposition of the derived category that has the correct length, and the K-theory of each factor looks like Z, but it's not coming from in a full exceptional collection. So, I guess you could say you have these line bundles L1, and this category AN is Ln plus a phantom. So yeah, so at least one of these categories will not have will still have the same K-theory, but won't be generated by an exceptional object. But the point is that there's this little lemma. So okay, you definitely can't have phantoms because a phantom cannot have it doesn't have any K-theory, so it just can't have a stability condition because because semistable objects have to have a positive central charge. So so phantoms can't have stability conditions, but also it's actually impossible to have a smooth and proper category whose K-theory is rank 1. And also, if it has a stability condition, then it has to be generated by an exceptional object. That's like a sort of little lemma. And so when you're engaging in the hunt for full exceptional collections and trying to study this phenomenon, if you only restrict yourself to semiorthogonal decompositions that come from paths in the stability manifold converging to some point on the boundary, if you restrict your focus there, then you're automatically get full exceptional collections as soon as you get a decomposition that looks like it comes from a full exceptional collection. So if you have a semiorthogonal decomposition where all the pieces have K-theory of rank 1 K-theory, then you have a full exceptional collection. So that's very helpful that'll be helpful. I'll explain a sort of conditional result about Dubrovin's conjecture in a second. So I just want to say, so just to return to the noncommutative MMP now that we have this perspective of this compactification and, how semiorthogonal decompositions are related to stability conditions. So in the first lecture, I sort of explained this conjecture of these canonical semiorthogonal decompositions up to mutation. And basically the key property is that if you have a birational morphism of smooth projective varieties, then you have this kind of refinement property that up to mutation, the canonical SOD for dB of x refines what you get by taking the kernel of pi star. Maybe this breaks up into more pieces too, and and the dB of y, you take the canonical semiorthogonal decomposition for dB of y, and so the conjecture is that this canonical mutation equivalence class of semiorthogonal decompositions has the property that it refines the one that you get from combining them like this. So that was fine, and you know, I was able to explain how just this compatibility under birational transformation is enough to, for instance, imply the d-equivalence conjecture and you know, non-commutative minimal models and that sort of thing. But it leaves a little bit to be desired in the sense that where are they supposed to come from, right? So where is a canonical semiorthogonal decomposition to come from? But now, after the lectures 2 and 3, we have a sort of program for producing these canonical semiorthogonal decompositions. Basically, what you're looking for are canonical paths in the stability manifold, I guess defined up to the action of C, that converge to a point in A stab, which is, I guess, one step more concrete than the original. So I mean, canonical SODs have been conjectured by Kontsevich recently. I mean, over the last couple years, and they sort of you can motivate them from non-Calabi-Yau mirror symmetry, again from this LG perspective, that if you have a non-Calabi-Yau variety, its mirrors may be some kind of LG model, and then the LG model has this sort of canonical, if you scale the potential, the LG model will have these canonical semiorthogonal decompositions for the Fukaya-Seidel category. So it's motivated by irresymmetry. You might conjecture that varieties have canonical SODs, but now there's a slightly more concrete way to say it, which is that you're looking for canonical paths in the stability manifold, and that just those paths alone will give you the semiorthogonal decompositions. So where do the
before you go, yeah, I forgot. Sorry, the topology, you said that the corresponding topology is weaker.
Well, no, there is one that
is it a metric topology? Because you said that it's already Hausdorff.
It's Hausdorff, yeah, but so it's not. I don't have a global metric on it. I'm not sure. I mean, yeah, I'm not sure. It has these local charts, these local U's, and I guess it's possible that those are kind of metrizable.
Yeah, I mean, kind of. There are some in a different kind of area of mathematics. There is something called Gromov-Hausdorff convergence, yeah, which appears also, that in mirror symmetry. The limiting object, they are not really complex object of algebraic geometry. They are sort of topological manifolds only. But somehow this limit, it makes sense from the physics point of view, and it corresponds to certain filtration of superconformal field theory. So I'm just wondering whether but if it's not metric, then maybe it's premature to make this speculation. Okay, sorry.
Yeah. It's not obviously metric. I mean, it's an interesting question, but I'm not sure. Yeah. So, but for finding paths in the stability manifold, basically we have this Bridgeland's theorem that says that the forgetful map that takes a stability condition to its central charge is a local homeomorphism. And here I'm imagining that, in the geometric setting, the Chern character is just the usual one. So H-alg is the I just define it to be sort of the image of this. Usually you do a twisted Chern character, but it's the image of this map to the cohomology. So that's what I mean by H-alg, and then you have this local homeomorphism. But we do have sort of so basically what we're looking for I mean, you can do it in the dual of H-alg, but under Poincare duality, you might as well just work in H-alg itself. We're looking for paths in H-alg, or its dual, that lift to stab of X. Right, so basically, the Bridgeland's theorem tells you that a path in the stability manifold is just a starting stability condition, and then a path in this vector space that lifts. So it's getting much more concrete where our semiorthogonal decomposition should come from, and there's already a well-motivated source of these paths, which is the quantum differential equation. So basically, I'll go. I'm giving a somewhat high-level description here, but I just wanted to give you a sense. So basically, you have these operators on the algebraic cohomology, and they depend on a parameter that basically lives in it's a complexified Kaehler class on X. So there's a omega, I'm imagining, as an ample class. Then you can also add some imaginary part if you'd like, IV. And you think of this as living in the quotient of the complexified Narron-Severi group of X, quotient out by the 2 pi I times the integral classes. And that's because the way psi appears in the formula, it's always e to the psi dot d, where d is an actual curve class. And so, B, it only really makes sense to say B up to translation by an integer cohomology class, 2 pi I, up to 2 pi times an integer cohomology class. B is only really defined up to that ambiguity. In any event, you have this operator for any parameter psi. You have this operator. It's something like the Euler field, and it's basically just multiplication by C1 of the tangent bundle, the first Schrödinger class of the tangent bundle, and then there's a formal sum. So usually it's formal, but I'm going to include, this is the sort of non-traditional requirement, but basically you take a sum over different homology classes in X, effective homology classes, and this is the formula, and right, so these operators here, basically, these TDs are just operators coming from the virtual fundamental class. M02 of X bar counts curves. It's the Kontsevich moduli space of curves of 2 marked genus 0 curves of class D, and this maps to X squared, and I can think of that as an operator from the cohomology of X to itself. It's a kind of a correspondence. And so I have this sum of operators. Now, usually without this box condition, this is a formal sum for a general manifold. So for Fano manifolds, there are finitely many, but then also for arbitrary manifolds, this by the cone theorem, this cuts you down. So basically, the cone theorem means you're cutting down to finitely many terms, and in some sense, I'm keeping the terms that are sort of largest. That's the intuition, is that I want to keep the terms that in this expression that are the dominant terms, and so right. So this is the quantum differential equation. So psi of t is you can think of it as valued in it's in the cohomology, the algebraic cohomology of X, tensor with C, and Z is just is another parameter, and mu here is a grading operator. So this is just some differential equation. It comes up naturally in in the theory of quantum cohomology is the Frobenius, it comes from the Frobenius manifold, coming from quantum cohomology, but for our purposes, it's just a very nice, honest, finitely many terms differential equation, and you can study its solutions, give you paths in the algebraic cohomology. And the proposal here is that basically so the sort of final version of this noncommutative minimal model program should be that there are canonical paths in the stability manifold that converge in this partial compactification. So they converge to an augmented stability condition. And the central charge of the path should look like, for these paths should look like this. And like I said before, basically, this path in the space of central charges sort of uniquely determines the path up to choosing a starting point in the stability manifold. So basically the same should be a point in the stability manifold, and then you kind of flow. So this phi t is a fundamental solution of the QDE, which means it's sort of a matrix which takes any class in the algebraic cohomology and spits out a solution of the quantum differential equation. And the conjectural formula for the central charge, and this comes from physics basically, is that the central charge should be the integral of these solutions of the quantum differential equation. That's the yeah. And
I'm a bit confused because you use E kind of.
did I
yeah,
I mean F, yeah, Z for F.
Yeah, it's
For F is an
different
object of the category. So Z of F should be so basically you have a fundamental solution of the QDE. That means that for every algebraic cohomology class, which is ch of F, you get some solution of the quantum differential equation. That's a path in the cohomology space. Now just saying you integrate that over X, and that should give you like a number, but a number that depends on T. And I'm saying that this is the central charge. As a function of T, the central charge will take any object and spit out this number. Does that make sense?
yeah, it does. The only thing I'm slightly confused with, you certainly prefer logarithms of central charges. So when you
Yes.
speak about asymptotic behavior, all right.
Well, it's yeah. I mean, so well, right. So I mean, yeah.
To
So in
define
the
this multi-scale filtration, you used logarithms.
right, when you look at the central charge, in sort of examples, like let's say, well, I think I'll mention this right immediately below. So, so can I let me just answer after
Sure, yeah.
saying what I meant to say. So, but I do have this other requirement that basically it converges to this limit point, and I want to be able to find objects that are sort of limiting to semi-stable objects in one of the subquotients that sort of represent every asymptotic class of solutions to this quantum differential equation. So that's a little bit vague. It's made more precise in the paper that I wrote about this on the noncommutative MMP. But you do need to require something like that in order to avoid a kind of trivial version of it. But a consequence is, though, if this proposal holds, basically then if this Euler operator has distinct eigenvalues for generic values of the parameter psi, and this proposal holds, in other words, and you're able to lift a fundamental solution, you're able to lift this formula for the central charge up to the stability manifold, then actually you do produce a full exceptional collection like this, where the log, this is the log of the central charge, has this form. In other words, the central charge looks like e to the alpha I, it's a constant. It's some constant. So it's saying that the z of the central charge is asymptotic to some constant times e to the alpha I over z times t. And this is what this is what the fundamental solutions of the quantum differential equation give you in the case where the Euler operator has distinct eigenvalues. It says you have like a sort of, a solution for every eigenvalue, and those solutions grow like e to the alpha I over z times t. In other words, their logs are growing linearly. Does that make sense?
Yeah, it does, but it's kind of simplest possible Stokes structure at infinity. Yeah.
Yeah, it's the simplest Stokes structure. Yeah. This is the simplest case. Yeah, when you have distinct eigenvalues. But the proposal is that maybe this is where you generate canonical paths in general. I mean, it's pretty speculative because I should say, like, stability conditions are only known to exist in very restrictive circumstances. So this is not. This is more of an inspirational kind of thing. It's a conjecture that I think will take many years to really figure out if this is what's going on. Because first we have to get a better understanding of the stability manifold. So yeah, there are more concrete things that you can extract from it. Like there's a version of this. There's a decategorification of these conjectures, which is very similar to the blow-up formula that's conjectured by Kontsevich and Katsarkov and Tony Yu and Pantev that he's been talking about for the last few years. They have this blow-up formula it's a decomposition for these Frobenius manifolds. So this is the decategorification of this thing is slightly different, but it's very similar. But it basically says that there should be some canonical decompositions of the Hodge structure on the topological K theory of X. That's the decategorification of a semiorthogonal decomposition or one decategorification is a decomposition of the Hodge structure on the topological K theory. And so this conjecture, that's much closer to being tractable because you now have this quantum differential equation in various, structure. They have the structure theory for ODEs of this kind, and you can ask, can you use this ODE to extract a canonical decomposition of the Hodge structure? So there are versions that are more tractable.
Yeah,
more accessible.
Yeah. And this blob formula, is it proven by Eritani or it's not? I'm kind of.
Didn't you say he's talking next week?
Yeah, but probably he will tell us. But
my understanding is that like a version of the blow-up formula is proven, and it's not totally clear if it's like exactly the version that
they wanted,
that they want or that they need in order to make their. I mean, they have these really cool applications to birational geometry and stuff like that. So I'm not sure if it's. Yeah, I mean, I've heard several talks about it, and I can't tell if Eritani's theorem actually completely does it or not.
Okay.
Yeah. Which is probably how you felt about it too. I don't know. I mean,
yeah, that's why I'm asking you.
Yeah. I think I have the same read. So, anyway, but back to the more speculative thing. So there's kind of a reason why this picture makes sense for this noncommutative MMP. This quantum differential equation thing. So the idea basically is that if psi, we said that psi is like omega plus IB, and if omega, the point is that if omega is large in some sense and close close to a semi-ample, in other words, if it's, so you're imagining having a birational contraction like this, if omega is really close to something that's pulled back from a very large ample bundle on Y, then E psi roughly only counts curves that are contracted by pi. So there's some sense in which you have this ample cone. So there's a kind of a sort of speculative picture where you have for omega in the ample cone, so you have the stability manifold. And then it has a sort of, it has this compactification to something that's conjecturally a manifold with corners, this augmented stability manifold. And there's a canonical component of the boundary. So for these, so you have these canonical paths that are always converging to a canonical boundary component. That's basically what this conjecture says. Because the boundary component, at least generically, will just look like this. And it basically will generically corresponds to a canonical SOD. And the idea is that, well, so all of these paths indexed by psi in the whose real part is Kaehler on X, we're going to limit to the same component. But then if you only count curves that are contracted, if you only count curves that are contracted by pi, you get to another component. So this is a related, if you look at a related differential equation, but only contracted curves counted by pi, this corresponds to some decomposition of this kind. So if you only count curves that are contracted by pi, you won't split up the derived category of Y at all, and you'll just maybe split up the kernel of pi star. And the idea is then you can think of it if you start with a semi-ample class on X, and you look at the corresponding operator, you'll end up limiting to some boundary divisor, which is a sort of coarser semiorthogonal decomposition. And then if you turn on, if you say psi is like a semi-ample plus a small ample, then you'll end up actually flowing into this codimensional two part, which actually sits on this canonical divisor. So that's the picture of why. So, the idea is if you have this differential equation and all of a sudden you add a very small, so you have a differential equation that has a limit on one component of the boundary, but if you turn on a little small perturbation of it, now instead of flowing into that component, it's going to flow into the intersection of that component with the canonical boundary component. Anywho, so that's the cartoon picture of what the NMMP is really saying. Is that you have this canonical component, and then all of the different birational contractions correspond to other components of the boundary that actually meet the canonical component. That's basically all it says. Okay. So that's like I said, like not, it's not very accessible as a mathematics. So I wanted to talk about some more concrete applications. So I made this conjecture. Oops. Let me give myself more space. So we had these open subsets or if you fix a multi-scale decomposition, you get an open subset of this of A stab. And then there's this sort of log central charge map. So if you take a collection of objects that give you a basis in K-theory, you get this log central charge map, and the image lies in these sort of canonical open subsets that sit inside the real-oriented blowup, of this moduli space of multiscale lines. And these things have explicit coordinates. I mean, they sit over this, they're the sort of real-oriented blowup of U gamma of sigma. And these, remember, sits inside of, you have some number of copies of C star, and then you have some number of copies of C, and then you also have you have some additional, I can't remember, was that notation? So these are like plumbing coordinates. And the SNC divisor just corresponds to the vanishing of these of this last coordinates. That's when the multi-scale line with mark points sort of breaks into a large, a deeper a tree with more and more levels. And so it's a relatively concrete space with coordinates, and the conjecture is that this is a local homeomorphism. The local homeomorphism. So the most immediate application of this is that it gives you sort of local coordinates on the stability manifold in a neighborhood of infinity. So if this conjecture holds, it should allow you to really get, like in the case of P1, the usual description of P1 is like, what Jan was saying, you have these chambers and then they're glued in this funny way. But if you use this, if you go to this other coordinate system that sort of corresponds to a neighborhood at infinity, you get a much more global coordinate system that includes some glued stuff and some non-glued stability conditions and all that stuff. So the most concrete thing is that this might be a tool for understanding the structure of the stability manifold at infinity. But as I was investigating this, I realized that there's a much more surprising application. So I wasn't sure if this manifold with Cornell's conjecture was easy or not, but then I noticed that there's this application. So let me tell you what it is. So if you have a smooth and proper DG category, it's a little bit of a different flavor, but if you have a smooth and proper DG category of a field, let's say K is equal to K bar, then the kinds of things that people have used stability conditions for have to do with moduli theory and studying birational geometry of moduli spaces. I alluded to this in an earlier talk, but basically, if you have this category, you have a moduli functor. So it takes the moduli functor, you should think of it as taking schemes up, I guess, to infinity groupoids. And basically it assigns every scheme to the set of isomorphism classes in the base change of the category to T. So a more concrete example, if C is equal to, this may be called C, the base change to T. So if C is dB of X for a smooth and proper scheme over X, then CT is just dB of XT. And so so basically this gives you some moduli functor, and a result of Tohen and Vauquier is that this is this as in a very abstract setting, in the setting of higher derived algebraic stacks, this is actually an algebraic stack if C is a smooth and proper category. But that's not, I mean, that's useful for some things, but not for all things. So if you want to actually produce a space, then you need to get something more concrete. So the more concrete thing that you can do is I can define if you have a stability condition, and if I take a class in the charge lattice, I can define this substack.
Daniel, could you explain the functor?
What?
M. Could you explain the functor M? You have the functor X, or those you regard as a triangulated category and should be exact functors.
This is
so
the functor.
roughly speaking, it's equivalence classes of families of DG categories. But if you try to make sense of it, you arrive to
Here T should be the DBT, right?
What? No. I'm saying the moduli functor is okay. So the moduli functor is supposed to make sense that you have a category C, and the question is, what does it mean to have a family of objects in C?
Mm-hmm.
And the answer to what it should have to have a family of objects in C is the same in having an object in this base change of C to T.
That's right. I mean, geometrically, that's the base change, but categorically,
What do you mean? What do I mean by this tensor product?
for the right-hand side of the tensor products, you have the
This
functor.
Yeah, there's an equivalent for this.
functor.
Yeah, and this is smooth and proper. It's just equivalent to saying you have these exact functors from C opposite
Exact
T.
functors.
Into perf. Oh, I see what you're saying. Into perf of T. Yeah. Sorry, that was a typo.
That it's a perfect T. Okay, thanks.
Yep.
Yeah. And the tensor structure doesn't have any, the perfect C doesn't have any role to play, or
No,
just a triangulated structure.
Yeah.
Okay. Okay, thank you.
I mean, it's important. I mean, perf T is a module category for perf K. So there's a K. You have to think of it as a K linear category, not just as a triangulated category. So really, I should be saying like sort of K linear exact functors. But anyway, okay. So but there's a more concrete thing, which is I can take the substack. And this parameterizes families. So of semistable objects in C heart of class V with of Turing class V. So basically, this just means that I can take an object in C sub T. So I can take if I have some sort of family E in the base change C sub T, I can now restrict it to every point in T. And just for simplicity, if K is algebraically closed, you just basically get a bunch of objects. If I do every closed point in T, I get a bunch of objects in my original category, and I consider only families where each of those objects that you get by restricting to every closed point in T is happens to be semi-stable and lies in the heart of the T structure for the stability condition. And when is this a reasonable? The question is basically, when is this a reasonable thing to do? So that cuts you down to a much smaller functor, and it's much more likely to sort of have a moduli space. So the examples where this comes up a lot. So examples are for K3 surfaces. This has actually been very useful. So Bayer and McCree basically studied the minimal model program for moduli spaces of sheaves. So this is a very useful tool. So for dB of K3, all the stability conditions, actually this moduli functor of semi-stable objects for generic stability condition will just be a sort of hyper-Kaehler variety if V is a primitive class. But and so for some of these stability conditions. The variety just corresponds to the moduli of sheaves stable sheaves on the K3 surface, which is a very commonly studied class of hyperkähler manifolds. And then Bayer-McCree said, well, actually, if you work with other stability conditions, you can understand all of the different birational models for these moduli spaces. So in some sense, they kind of completely solved the minimal model program for these particular kinds of moduli spaces. They described all minimal models.
Anything interesting for abelian surfaces, or just all classical?
I don't know. Yeah, I guess probably. I think probably somebody's extended to abelian surfaces, but I don't know off the top of my head. Yeah, I mean, the extension that I do know about is you can. There are other categories which look like dB of K3. So you have these Kuznetsov components. So inside dB of a it's like a cubic fourfold, right? What was it? Is it a cubic or a quartic? Oh my gosh, I'm having like a weird. I think it's a cubic. So anywho, you get these two exceptional objects, and then a piece that's a CY2 category. It's a Calabi-2 category. And basically, the people in this area, like Alex Perry and Xiaoli Zhao and those folks, have been able to study moduli spaces. In A, give you other hyperkähler varieties. So you can sort of extend this story to study, to use moduli theory, or the moduli theory for Bridgeland semistable objects, to study other hyperkähler varieties that are sort of deformations of these moduli sheaves on a K3. And so the surprising theorem is that if you have this smooth and proper category, maybe it's not surprising. If you have a smooth and proper category and you have a generator, then the following are equivalent. So if there exists some function that allows you to upper bound the Homs, and that function only depends on the masses, I guess this should be an increasing function. Well, that turns out that that's the same as this moduli functor that parameterizes semistable objects in the heart. So here, this is for a stability condition. That's equivalent to this moduli functor being of objects in the heart being an open substack with affine diagonal and having a proper good moduli space. So it's a sort of very general thing that a general principle is that you should, if you can cook up an upper bound on Homs, then you can automatically for free get the existence of moduli spaces for semistable objects. So the reason I mention these examples is that this is a sort of industry. People have been using stability conditions to study moduli spaces, and it's usually a pretty hard thing to check that your stability condition actually gives you moduli spaces. You know, for basically only when it's sort of comparable to Gieseker stability, and then you make some wall crossing arguments, et cetera. But this is a very different way of proving the existence of moduli spaces. So what does this have to do with the manifold with corners conjecture? And the idea is the following. It's actually a much weaker version statement than the. Sorry, can I take an extra minute or two just to finish this thought, Jan?
Sure, absolutely, yeah.
Okay. So the final thought is so what does this have to do with the manifold with corners conjecture? So I can take my generator G in the category C, I can regard it as a functor from dB of k to C that takes the ground field k to the generator G. And using this functor, I can glue to get a semiorthogonal decomposition where this is a single exceptional object. And then you have the original category C as a semiorthogonal factor. And then I can mutate. So I have this left mutation functor, which is like an equivalence from C to C prime. And using this equivalence, I can do two things. I can glue. So I have I can use this equivalence to transport my stability condition sigma. Will now be in the stability manifold of C prime. And basically, you can have this little lemma. Is I can glue stability conditions. So I can glue sigma to a sort of trivial stability condition. On D. So basically, so basically, if you just declare that E is semi-stable and phase of E is very, very negative, you can get one stability condition. I'll call that sigma tilde on D. And you can also glue sigma prime. Oh, and this is using the semiorthogonal decomposition E comma C. And if you do the same thing with C, you can glue it using the other decomposition. And here you can glue it as long as you declare the phase of E to be very, 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 very positive. And the little lemma says that if there's a path connecting sigma tilde and sigma tilde prime in stab of D, then there actually exists a constant such that hom of G comma F is less than or equal to C times M sigma of F for all F in C. So you get this this very appealing looking bound on Homs just from the fact that these two glued stability conditions should be connected by a path in the stability manifold. So what does that have to do with the manifold with corners conjecture? Finally, if you believe that the manifold with corners conjecture holds for D, I can look at stab D. And the idea is that there are these regions, just like in the picture for P1, you should have a region that's glued for the SOD E comma C, and you have another region of glued stability conditions for C prime comma E. And somewhere in here you have sigma tilde prime, and somewhere in here you have sigma tilde. And I'd like to show that there's a path connecting them. Well, unfortunately, these glued regions don't overlap, and so I don't know that I can get from one to the other. But if this was a manifold with corners, and I look in the neighborhood of this limit point that lies between the two glued regions on the boundary, well, then the manifold with corners conjecture says that this here this region here is actually honestly a disk. So there really is a disk of or a half disk of stability manifolds that overlaps with both glued regions. And then I get a path by going into this disk, crossing over and coming out there. So it's a very, very mild, so manifold with corners is a very specific thing, but it turns out that it implies that these glued regions for these two mutated semiorthogonal decompositions are connected by a path on the stability manifold. That in turn is enough to imply this inequality, and this inequality is enough to plug into this theorem. This inequality gives you this bound, basically, upper bound the Homs. In this case, the function f is just a multiplication by constants, a linear bound, and that gives you the existence of moduli spaces. So, so I was a little bit surprised when I realized that this manifold with corners conjecture actually implies this very general existence statement for moduli spaces, which I think is very cool. But it also convinced me that the manifold with corners conjecture is like a little bit subtle. I've been thinking about it a little bit. There's like sort of maybe some approaches or whatever, but nothing to report so far on the manifold with corners conjecture. Okay, I'll stop there. Thanks for letting me go a little bit over.
Yeah, thank you very much. So yeah, kind of very entertaining last lecture.
Yeah.
Yeah. Actually, I have a couple of questions to the previous parts of your talk. You
Sure.
mentioned some other people who introduce this multi-scaled stabilities, and I Googled. I know 2 out of 3. I know Barbieri and I know Martin Müller. But I looked at they also interested in compactification of the moduli space of stability conditions. So either somehow related to what?
Yeah, I have to be, it's a little bit, I'm embarrassed to say that I haven't taken a close look at their paper. But I think that theirs is more specific to the case of when, when you have these, there are certain cases where stability manifolds are kind of, can be identified with spaces of quadratic differentials or something like that. And then, so if you have an explicit description of a stability manifold, you can then consider of this kind, you can then consider compactifications of the kind that those guys study of curves with some kind of differential, and then
I see, but no categorical, probably this categorical story which you developed.
Yeah, I don't think it's the same. Yeah, I don't think it's I don't think it's the same. I think theirs is related more specifically to when you have an explicit description of the stability manifold.
I understand. Yeah, somehow I think I told you in my that I was interested in this compactification of the moduli space of stability condition, but on some Fukaya related to the Fukaya category of on certain Calabi-Yau threefolds, non-compact kind of conic bundles or spectral curves, and spectral curve it's quadratic differential, so that's probably they do some geometrics. Okay.
Yeah, that's probably more closely related to what they're doing. Yeah, exactly.
Yeah, and yeah, the case of P1 is very nice when you can write down explicitly everything, and is it the only known?
You'll have to ask. I mean, so it's the only one that I'm very versed with, but it's the but my student Alekos, who gave the second talk, has been developing lots of other examples. So he has a lot of other kinds of canonical quiver, other kinds of quiver examples, basically, where you can describe the compactification very explicitly.
Curves,
and then
other curves.
Other curves, actually, you don't get stuff that's very interesting because they don't have. So there's another point in the stability manifold of P1. There's actually a large volume limit point. Basically, there's a point in there's a point in the other direction over here, which is isolated, because the filtration basically corresponds to filtration by the dimension of the support of a complex, and that filtration, the category is not admissible. So you have this isolated point, and for other curves, that's the only point that you have. So for other curves, you just have the region The stability manifold is just the coherent sheet, is just slope stability, and then with a single point, I think a single point at infinity, that's this kind of large volume limit point. But I'm interested in, I think P2 would be a good example next, because people have thought about that, but then, but I know that Alekos is actually working on many different projects really. So maybe you should have him come speak once he gets those things finished, and he can tell you about more explicit examples.
Okay. All right. So maybe we should ask other people, maybe some questions from the audience, from other people. So surprisingly, the audience is quiet. Well, or maybe not surprisingly.
Yeah.
Okay, now here my mic.
Okay. Yeah. I was waiting, Zhongzhu, when you will start to ask your question. So go.
Okay, here is my question. On Monday, you remember you talked about the break group action on this permuting and kind of a mutation. So that changes the special connection, exceptional connection in a certain sense. So does that, can that be lifted in some sense in the space of the break group action on the space of stability conditions?
Well, it doesn't really act on the space of stability conditions as far as I know, but it acts on the boundary. If the sort of manifold with corners conjecture is true, it sort of says that with the two-term semiorthogonal decomposition, you just get this kind of you just get the braid group on two strands. So you just get Z acting, and that's the group of deck transformations. And you have all these different, basically you have all the different, you can keep mutating the semiorthogonal decomposition. Oopsies. Oops. Okay. Well, okay, that computer just crashed. Anyway, you can keep mutating the semiorthogonal decomposition. When you have like a 3 or more term, you get this entire the boundary in general, each component of the boundary looks like some kind of universal cover of each boundary component looks kind of like the universal cover of some moduli space of marked curves times the stability manifolds on each of the factors in the semiorthogonal decomposition. So basically, yes, you get if you take P1 and remove n points, you take the universal cover of the mapping. I mean, you basically take the Teichmuller space for that thing, and the boundary will be like the boundary component will be like a product of that thing, and the stability manifolds on the factors.
I see.
Yeah.
Because in cases of a quiver, representations of the category of representations of a quiver, and so this kind of in some many good cases, definitely including the canonical quiver, which corresponding geometrically to the P1, and that's this is called a GBP reflection, which is changing the quiver, but the derived categories are somehow giving an autoequivalence, and which are changing the exceptional connections. Changing the generators of the category.
Yeah.
So in the quiver case, how this break group action related to the GBP reflection functors, probably haven't thought of that.
Yeah, I'm not sure. Yeah, I don't know. I mean, in general, you don't really get autoequivalences of the category. I think you need a little bit more to get an autoequivalence of the category.
No, it does not get autoequivalence, but kind of transforming one category to another category, because underlying quiver is changing.
Yes,
but what is interesting that it maps a certain set of indecomposable modules two indecomposables or being killed.
Hmm.
And that gives so for the people working on representations of algebra, they're describing all the indecomposable in terms of Auslander Latin quiver. And they have this kind of translation. So those translation now fill in the P1 case, which is the Bridge group action. Moving along, and that get kind of a infinite long sequences. This is the Bridge group, because in this case doesn't have a finite order and keep on going. That's a Z action.
Right. Yes. Yeah, it is possible. Yeah, this thing will detect actually if you have finite order, this compactification. But basically, yes, I think that in those quiver examples, it will correspond to sort of different chambers on the boundary. So the boundary sort of naturally has some kind of chamber decomposition, and the group will act on the boundary in a way that kind of moves the chambers around.
Okay. Okay. Well, thank you very much. Really appreciate the talk. It's very inspiring.
Okay. More questions? Well, if there are no more questions, so Daniel, thank you very much.
Thank you.
Nice lectures, and there are a couple of preprints in the archive people can look at.
Yeah, and most of it, it's still, we're still finishing the paper that does the compactification, but that will be up hopefully soon.
Okay. All right. Thank you. And if there are no more questions, this is it for today. Thanks.
All right, thank you.
Bye.